Looking at part B, you can see we have x to the fourth power. We want to identify not the perfect square now, but the perfect cube factor and the trash factor. Using my sort of heuristic rule up here, if we look at the definition of the root and the exponent for some variable expression like this, we can actually write it as an exponent. While 4 divided by 3 would give me some kind of fraction still, that means that this technique is really not that useful. But it does give me a sense of how to approach this problem using factoring. X to the fourth is really just x multiplied together 4 times. And so when we ask what are the perfect cube factors inside this expression, we're looking for triplets. Looking right here, I've got at least 3 x's, and of course 1 being too many. If we factor into x to the third power times x, one of these becomes a perfect cube that would make the exponent divisible by our index. So we just toss one of our exponents away so that we can make it divisible by the index. That way, when we go to find the cube root of this expression, we can split it up appropriately into our perfect nth factor and our trash factor. So the cube root of x to the fourth becomes the cube root of x to the third times the cube root of x, where we can use our definition of the root to answer the first question. What raised to the third power gives me x to the third? So the exponent and radical here match. They'll cancel each other out, leaving me with x times the cube root of x for the solution. A similar scenario can be seen in part C, where again my exponent, 7, is not evenly divisible by 4. However, if we factor it in this case, we'll find that x to the fourth times x to the third is how we want to split this up. So the fourth root of x to the seventh will split into the fourth root of x to the fourth times the fourth root of x to the third. So the fourth root of x to the fourth is just x, and fourth root of x to the third is what we threw in the trash. It stays underneath the radical just like that. So we've seen how to utilize our definition of the radical as well as this connection to the exponent to be able to answer questions about numeric values and variables. So let's look at a combination of the two now. So take a look at part A here. I'm asked to find the square root of 32y to the fifth. So this is where this technique actually comes in handy because it can be kind of difficult to identify all the sort of parts and pieces of this that we want to remove. So again, I'm interested in identifying my perfect square expressions inside that radicand, as well as what I'm going to toss away or put in the trash can. So thinking about this one piece at a time, I'm going to start by considering what are the perfect factors inside of my coefficient, 32. Again, if it's not obvious, I can use some version of prime factorization to get at that answer. So for instance, looking at 32, I might think, well, that could be 4 times 8, where 4 is a perfect square. However, there's still another perfect square hidden inside this expression. 8 itself has another perfect square hidden inside of it. So my perfect squares here, if we multiply them together, will give me the largest in the expression. So at least partially, 16 is my perfect square and 2 is my trash factor, at least for the coefficient. For y to the fifth, again, if we want to factor it, we can think about it in terms of this expanded form and recognize that a perfect square would be represented by at least 4 of these y's duplicated. So y to the fourth is my perfect square factor, and y gets thrown in the trash. Now we've identified the largest perfect square factor and the non-perfect square factor of this expression. So when we go to find the square root of 32y to the fifth, we'll split it up into two parts. square root of 16y to the 4th times the square root of 2y. So in this case, we can identify, again, what the square root of our perfect square factors are using the definition of the root. What raised to the second power gets me to 16? What raised to the second power gives me y to the 4th? And our perfect square factors pop out from underneath the radical, where our trash factors stay within. So there's my solution. In part B, we can follow a sort of similar pathway. In this case, though, we're looking at the perfect cube instead of the perfect square factors. So I might start again by identifying what the perfect cube factors are for the numeric value, 54, and trying to split it up one little piece at a time. So perfect cubes and trash factors. 54 in this case, I could factor in a couple different ways. This would be something like 2 times 27. And 27 happens to be a perfect cube, but if it's not obvious in this case, we might multiply it out as 9 times 3. 9 is 3 times 3. One more 3 gets me to a perfect cube. And so for my coefficient here, I'll write 27 in the perfect cube box, and 2 is going in the trash. P to the 10th, I'm not going to write out all the p's here, but that's 10 p's multiplied together. And so p to the 9th times p to the 1st would be how we split this up so that we have a perfect cube and a non-perfect cube factor. Once we split those apart and give them their own radicals, the cube root of 27 p to the 9th would give me 3 p to the 3rd. And of course, we keep our non-perfect cube factor under the radical. For our solution, 3 p to the 3rd times the cube root of 2p. So this perfect square and trash factor technique can be utilized in conjunction with prime factorization and a solid understanding of the connection between exponents and roots to make quick work of problems like this. Let's look at a few more. Here's probably the most complicated version of this question that asks me to just reduce some expression. So let's look at part A here. I'm asked to identify from the expression 63, u to the 3rd, and v to the 5th, what are the perfect square factors, what is going to stay underneath the radical. And just as before, I'm going to start with thinking about the sort of coefficient here. 63 happens to factor to give me 7 times 9, where 9 is a perfect square and 7 goes in the trash. U to the 3rd, v to the 5th. Neither of those exponents are divisible by 2, and so we would split them up such that we make the exponents evenly divisible by 2. So we could split these into u squared times u. V to the 5th we could split up into v to the 4th times v to the 1st. Notice that I don't need the index and the exponents to match to make a perfect square or perfect cube. I just need them to be divisible by that number. So we leave u squared and v to the 4th in our perfect square box and throw away at least one of each. So now when I finally find the square root, again, we split this up into two parts. We take 63 u to the 3rd, v to the 5th, and split it up into the square root of the perfect square factors times the non-perfect square factors. What's the square root of 9? 3. Square root of u squared is u. Square root of v to the 4th is v squared. Our trash factors stay underneath the radical, and so there we have our solution. Similar scenario again for part B, only again the index is now changed, and so we're looking for perfect cubes instead of perfect squares. If I want to split apart again my coefficient 40 here, I can think about just breaking it down into something like 4 times 10. Now normally we would identify perfect cubes here, so I'm interested in breaking this perfect square down further, 10, for instance, could be broken down into 2 times 5. And so it becomes apparent that 8 is my perfect cube and 5 is my trash factor. With x to the fourth, I want to split it up into x cubed times x. Y to the fifth, we're going to break up into y to the third times y squared. All of those in mind, we keep our perfect square factors together. So again, our expression splits up into the following. We get the cube root of 8 x to the third and y to the third multiplied by the cube root of 5x and y squared. So the cube root of 8 is 2, cube root of x to the third is x, cube root of y to the third is y, and we leave our trash factors underneath the radical, so we have 5xy squared. So there's my solution. Again, this factoring process using prime factorization, looking for duplicate factors to make the perfect square or cube term that I'm interested in, can make quick work of these types of problems. So let's look at another type scenario where instead of wondering how to split an expression apart using factoring, I'm asked to do so using division. This is the quotient property, which works a lot like the previous section. However, now we're talking about division. So the process is very similar. I start with some expression, the nth root of a over b. And I'm capable using this property of splitting the numerator and denominator up on their own. For instance, in part A, I'm asked to find the square root of 9/49ths, which sounds kind of complicated. Dealing with fractions generally is an anxiety-inducing experience for most students. So to use our definition of the radical here, what raised to the second power gives me a fraction can be kind of an intimidating question to pose. With the quotient rule, however, I can split this up a little bit easier. We can take the square root of our fraction and turn it into the square root of the numerator divided by the square root of the denominator. Since the square root of 9 and the square root of 49 are both perfect square terms, we end up with a solution of 3/7. And this answers the original question I might have posed. What raised to the second power gets me back what's under the radical? So 3/7 is the solution. In part B, we're looking at the square root of 0.16, which we'll move over here and maybe re-express this as a fraction like 16/100. In this case, again, we can split the numerator and denominator up and get a solution pretty quickly because our two expressions are now perfect squares. So the square root of 16 is 4, square root of 100 is 10. So 4/10 is technically our solution. However, we could reduce this to 2/5. So the quotient property allows me to split, again, my numerator and denominator separately so that I can apply either my definition of the root, or on some occasions, we'll actually still have to use the product rule to finish a problem dealing with division. So let's look at a few more examples. Look at part A, for instance. I'm asked to find, in part A, the square root of 45/80. So the first thing I might do here is not actually apply the quotient rule. It's actually going to be to consider how this expression, 45/80, might reduce. In other words, 45 and 80 surely have a common factor that I can take advantage of. So for instance, 45 is the same as 9 times 5. 80 happens to be 16 times 5. By reducing the fraction before I apply this quotient rule, I make for much quicker work of the problem. So reducing this to its following form, 9/16, we come up with the same solution we did a moment ago. Now we can apply the quotient rule and finish the problem using the definition of the radical. We end up here with a solution of 3/4. Let's use as well some of our exponent rules to look at an example with numeric, or excuse me, not numeric, but variable expressions. Take a look at part A here. I'm asked to find the square root of m to the 6th divided by m to the 4th. Again, I would not necessarily want to split this up immediately and find the square root of m to the 6th and square root of m to the 4th, although that's fairly easy in this case. The expression here can be reduced by subtracting the exponents. If you have the same base for exponents, our heuristic for finding the solution is just to find the difference. So I can actually reduce the problem here to just the square root of m to the 6 minus 4, or m squared. What raised to the second power gives me back what's under the radical? Well, just m. And so I get a solution pretty quickly here, and I don't actually have to find the answer using the sort of quotient rule. Now let's combine the two ideas. Here's some scenarios where I have both a numeric value involved as well as some variables. Let's take a look at part A. So I'm asked to find the square root of 45 x to the 5th and y to the 4th. Unlike the other cases, there's not really anything that I can do to reduce the fraction, and so I can immediately apply my quotient rule. So we end up with the square root of 45x to the 5th divided by the square root of y to the 4th. My numerator in this case, I'm actually going to have to use the product rule on to simplify. Neither 45 or x to the 5th are perfect square terms, and so we'll need to split them up so that we can identify their perfect square factors and the trash factors. My denominator, however, is a perfect square. What raised to the second power gives me back what's under the radical in that case? Well, it should be y to the 2nd. Again, if I divide the exponent by the index of the root, I'll get my solution. So what do we do with the numerator? Again, we use the product rule to split the numerator up into perfect squares and non-perfect squares. So what's going in my perfect squares and what's going in the trash? 45 could be broken up into 9 times 5. X to the 5th could be broken into x to the 4th times x. With that now split, we can answer the question of what's the square root of 9x to the 4th using our definition of the root. And we get something like 3x to the 2nd times the square root of 5x, all divided by y squared for the solution. So even working with quotient problems, on occasion we'll still need to use the product rule. So it becomes critical to understand how to utilize the specific techniques here quite quickly, because we need to be able to work out the answer even while solving a much larger problem. And that's usually the case of how these will be presented. Let's look at another example here. And this is probably the most difficult version of this question that could be presented. So I'm asked in part A here to identify the square root of this quite large expression, 18 p to the 5th q to the 7th, all divided by 32 p to the 1st q to the 2nd. And my first task is really going to be, again, to identify how is this going to reduce. Before I apply any of my quotient or product rules here, I want to try and reduce the expression as much as possible. So for instance, 18 and 32 seem to have some common factors. In this case, we could split this up as well by reducing the variable terms. P to the 5th divided by p. Again, we would subtract those exponents to make quick work. 18 we could write maybe as 9 times 2, 32 as 16 times 2 to discover that they have a common factor. Again, reducing the fraction for the variable terms just involves subtracting their exponents. So we get p to the 4th and q to the 5th when I reduce. Canceling out my common factor with the numeric terms then allows me to split these up into the numerator, 9p to the fourth q to the fifth, and the denominator, square root of 16. So all of this in pursuit of reducing the expression as much as possible before we apply this quotient or product rule. So the square root of 16 is 4, but my numerator needs to be split up. We would have a perfect square, bunch of factors, and my trash factors. 9p to the fourth and q to the fourth times the square root of q would be how I suggest splitting this up. Again, we're just identifying what is the largest perfect square factor in the bunch. So now we can finish the problem off. We've got square root of 9 is 3. Square root of p to the fourth, q to the fourth is p to the second, q to the second. Our square root of q stays underneath the radical, and then all of that gets divided by 4. So there, finally, we get our solution. Clean it up just a little bit. And again, it takes a little while to get the hang of how to identify perfect cubes, fourths, or fifths. Instances where we're interested in doing so, just remember that we're looking for duplicate factors that represent those certain ordered terms.